lesson is on synchronous counters. In this lesson, we're going to look at what synchronous counters are, and then we're going to look at some examples of 3-bit and 4-bit synchronous up counters, as well as examples of 3-bit and 4-bit down counters. We're also going to learn how synchronous counters can be implemented with medium scale integration using MSI gates. So first, let's define synchronous counters. In a synchronous counter, all flip-flops are simultaneously clocked by an external clock. In asynchronous counters, what we witnessed was that we were clocking the flip-flop from one to the other instead of connecting them all to the same clock. Synchronous counters are faster than asynchronous counters at simultaneous clocking because they're all synced to the same external clock. Synchronous counters also don't have that ripple effect that we saw asynchronous counters have, and they do require more logic. So let's take a look at the theory behind a 3-bit synchronous up counter. So what we're seeing here is a timing diagram. This is just like in the graph where you guys see in Multisim Live. So at the bottom we have our clock, which is a constant signal. This clock will be connected to all of the clocks and all of the flip-flops. What this resulted in is that Q0 would toggle on the falling edge of the clock. So that's what we see right here with these red arrows. That's the falling edge of the clock signal is triggering Q0. Now Q1 is going to toggle on the falling edge of the clock and when Q0 is equal to 1. So when we have a high signal. So that's these purple arrows that we're looking at. Q1 is only responding when the clock is at its falling edge, so right here on the falling edge, and when Q0 is high. When we hit a falling edge of a clock and Q0 is not a high signal, nothing happens at Q1. It's only when we have the combination of the falling edge of the clock and the high signal in Q0. Then we have Q2, which toggles on the falling edge of the clock when Q0 is 1 and Q1 is 1. So if we look at Q2, that's the green arrows. So we have the falling edge of the clock, Q0 is at 1, Q1 is at 1, then Q2 triggers. It does not trigger until we have all three of these. This at the falling edge, this on high, this on high. It doesn't trigger again until all three of those occur at the same instance again. So that's not until way over here where we have a falling edge, Q0 is at high, Q1 is at high, Q2 then triggers. So let's talk about the timing of the 3-bit synchronous counter, synchronous up counter. So in this diagram, you're going to see that we have 3 JK flip-flops. The big thing to notice here is that we have this external clock over here, and that clock is connected to all of the clocks on the flip-flops, okay? We then have the cues that are coming out to probes. You'll notice that they are all interconnected to, back here, to an AND gate, which then goes into the J flip-flop of this, or the J input of this last flip-flop. The K is then connected to the J. All right, and we also have this J connected to a lead on the flip-flop. That is circling around from the Q right here. All right, we then have the J set up right here, which is set to the clear, which is then set to a power. So this says 5 volts for us, that would be a digital constant. The clears are then interconnected between the 3 flip-flops. They are also connected to the digital constant, or what we would have as a digital constant in Multisim Live. So if this is an up counter, meaning we are counting up, this is how it's going to count. So this is 0 right here. All right, so we're starting at 0. This is that falling edge. So we hit the falling edge and Q0 triggers. That's counting the 1. We switch to 2 on the next falling edge of this when Q0 is a 1. That's when Q1 is going to trigger, and then we have the 2 time frame. We're going to go to 3 right here. So if we look right here, what's happening? We have the falling edge. We have this at 1, or we have this right here, triggering again at Q0. Q1 has not changed, okay? So we are still at 3. At 4, we start here. We can see that we have things happening on all of our probes. 5, right here through here. 6, and then 7. You'll notice this is not as tidy as the asynchronous counter. We don't have that ripple, so it's not like we're seeing kind of this falling wave of signals. Instead, we're getting what looks a little more sporadic, but it is all synced up on one to the other, and that's because they are all synced through this one clock. So this is when we have a 4-bit counter. So this is when we're controlling the counter with flip-flops, and we have 4 of them to create that 4-bit. You'll notice that we have the AND gate, and we have another 3-input AND gate down here. Okay, this flip-flop right here is going to toggle on with the falling edge of the clock. So when this has a falling edge coming into the clock, this Q0 is going to toggle on. This will not indicate and turn on until we have a falling edge of the clock, and this is turned on, so Q0 is on. Then these two will stay on. These two will just stay and keep functioning as they were. So they may turn off depending on when we hit falling edges. They may turn on again afterwards. We'd have to go back to that timing diagram and look at it. But Q2 will not trigger until we have the falling edge of the clock, Q0 is 1, and Q1 is 1. Then Q3, we need the falling edge of the clock, and Q0 at 1, and Q1 at 1, and Q2 at 1. So these are synchronous in the fact that they are all synced together, meaning they have to sync in order to have something happen. That's why we call it synchronous versus asynchronous, which they're more independent with that ripple effect. Okay, so now we're going to take a look at the theory behind a down counter. Okay, so we go 7, 6, 5, 4, 3, 2, 1, 0, then it resets back to 7. So if we start here, we have our clock signal. Okay, falling edge of the clock, Q0 is going to trigger, so Q0 started high, drops low. Okay, Q1 is going to toggle on the falling edge of the clock, and when Q0 is 0. So now that's this purple arrow. So this is falling edge, this is at 0. So this is starting at high and dropping to low. Okay, and then our Q2 is going to toggle on the falling edge of the clock, and when we have Q0 is 0 and Q1 is at 0. So that doesn't happen until right here. Falling edge, we're at 0, and then this drops to 0. Okay, this is going to continue to cycle in this way. So if we go here, okay, we only have an instance of red, then we have the purple, then we have the green again. So you can see it kind of builds on itself versus the ripple where it was like one, then the other, then the other. These are more stacked in nature. Okay, so this is what the actual circuit would look like for the 3-bit down counter. So what we can look at here is, again, we have the clock. That clock is connected into all 3 of the clocks independently. Okay, our clear goes to our preset, just like that. And then our top preset is set to a digital constant. And that is looping back around to connect to the bottom clear. The J and the K inputs are based on either the power, okay, from right here, or in this instance, it's coming around from this AND gate. That AND gate, if we trace it backwards, is coming in from the Q0 of the first flip-flop and the Q0 of the second flip-flop. Okay, we then have 3 probes out here that are attached to Q. Remember that this first flip-flop is going to trigger on the falling edge of the clock. The second one will trigger when the falling edge of the clock and Q0 are equal to 0. So that would mean the falling edge of the clock, Q0, 0, just to clarify. And then Q2 would toggle on at the falling edge of the clock, and when we have Q0 at 0 and Q1 is at 0. Similarly, we have the 4-bit synchronous down counter, so that's where we add that additional flip-flop in. You'll notice that we have this 3-input AND gate again attached to that 4th flip-flop. So we're adding a little bit more logic in order to have a 4-bit counter. So we have the 4 flip-flops. They're set up in the exact same way, except we're just adding this bit down here. So we're adding this 4th flip-flop and this 4th gate. Or the second gate, I should say. It's essentially got 3 inputs. So we have the 3 inputs, and it's going into here. So the sequence of how the J and the K are set up is slightly different because we have that 4th flip-flop. That they're going to trigger the exact same way. So falling edge of the clock, and Q0 equals 0. Falling edge of the clock with Q0 being 0 and Q1 being 0. Same thing here. We're going to end up with the falling edge of the clock in Q0 and Q1 both have to be 0. And then here it has to be all 3 of these at 0 and the falling edge of this external clock right here. Okay, so far what we've looked at is how we can control a synchronous counter using a JK flip-flop. Now we're going to take a look at how we can control asynchronous counter with the 74LS193. Now this chip is unique in that it actually works as an up counter and a down counter. Now there is the 74LS163, which is only an up counter. We're just going to skip right past that. It's not available in Multisim Live, and in my opinion it makes more sense to use the thing that allows us to count up and down by just making a few changes within the chip. So it has separate clock inputs for up and down counting. So depending on whether we want the counter to count up or down depends on where we place our clock. It also has a preloadable count start. We'll take a look at that when we look at the inputs. It also has an asynchronous load, which means the data from the inputs is automatically loaded to the outputs, and it has an asynchronous clear, meaning it clears automatically as well. We have a carryout signal for counter cascading up counter. So that means if we're cascading counters, meaning we're attaching them to each other in a way that allows them to go one right after the other, we have a carryout signal for if they're counting up, and then we have a borrow out signal for the same scenario if they're counting down. Now on the left, that's the component diagram. You'll see that we have 4 inputs. They're A, B, C, and D. And we have 4 primary outputs, A, QA, QB, QC, and QD. Here we have the load, the clear. This is our borrow out and our carry out, and we'll talk more about those in a moment. Our up and down clocks are over here. And then this is our connection diagram. So internally, we've got a whole lot of gates going on in here, and I'll show you that in a moment. You're not gonna be responsible to know the logic inside of there. I just want you to be able to see how it works so it makes sense. So you'll notice that we have outputs over here. We've got QB and QA on pins 1 and 2. Our data B input is right here. Okay, and then we have inputs for our clock, and then QC and QD are on pin 6 and 7. Ground and VCC are on 8 and 16, so we're pretty familiar with that. Our data and clear are on pin 15 and 14, and then we also have our load, our data C, and our data D as inputs across here. So 11, 10, and 9 are all inputs, and then the borrow out and the carry out are on the top portion. So we have it's a nice little pattern of output, input, output, and then input, output, input. So let's talk about the signals as they come in. So first of all, we have A, B, C, and D. Now signal A is our least significant bit. And then we have B and C, and D is our most significant bit. Now these 4 data inputs are the data that gets loaded to the counter. And these are also how our upper and lower limits get set, is using A, B, C, and D. Okay. Then we have our outputs, which are QA, QB, QC, and QD. Now this translates directly across. So QA is our least significant bit output. Then we have QB and QC, and then QD is our most significant bit output. So these are the actual count of the counter of these outputs right here. Okay. So next we have the up, and the up is the up counter clock input. So this is where we put the clock for an up counter. And the down, if we're using this for the clock, the down has to be held at a logic level 1. So that means we would attach this to a digital constant and make sure that it is at 1. Now, the reverse of that is that if we want this to be a down counter, we're going to put the clock on here, and then the up needs to be held at a 1. So whatever one we are not using to clock needs to be tied to a digital constant. Then over here we have the load and the clear. So the load is our load input. So when the logic is 0, the data on A, B, C, and D load into the counter. So that means they go bloop and come right over here. Okay, and this is asynchronous, so it happens automatically with the signal coming from the clock. We also have clear, okay, and this is so when the clear input is a logic level 1, the counter clears automatically. Again, the clear is asynchronous, so when we hit the logic level 1 for the clear, boop, gone, okay? Now, these two are the two that we are most unfamiliar with. So the CO is the carry out, so that is the carry output. Okay, and when the logic is 0, and the counter is at its upper limit, so 1, 1, 1, 1, 1, 1, if the counter is an up counter. So this signal is typically used when we cascade. So think of it as if we have one timer and then we're going to another timer to trigger it or get it started. That's called cascading. So we would use the carry out if it's an up counter. We use the borrow out if it's a down counter. So the borrow output is when the output is 0, when the counter is at its lower limit, so 0, 0, 0. And this is the counter that is used when the down counter is cascaded. Okay, now this is that logic diagram I was talking about. So this is what's actually happening inside of the chip. This is insane looking. I don't expect you to remember this, but there are some of you that don't, especially with the flip-flops, you struggle to understand kind of what's happening inside. So I did want to include this. So you'll see that depending on the input or output, we've got a series of logic following. So we have inverters, we have NAND gates, we have AND gates, we have OR gates, and all of them are going to a specific output on the other side. Okay, so this is just all of the logic that controls the inside of this chip. So this is essentially the electronic magic as it's happening. Okay, so now let's take a look at the timing diagram. So here we have our clear and our preset. So what we're looking at here is, if you look at letter A, clear is set to a logic 1. Okay, so that means it's a high. And the outputs are cleared immediately. Okay, clear is an asynchronous input. So that means it just happens automatically. Now, then we have the load. Okay, so if we look at B, load is set to a logic 0. So the outputs are loaded with the input data immediately, because again, that load is asynchronous. So in this case, 131101 is loaded as an asynchronous input. So that just, boom, gets loaded in there, 1101. The next portion that happens is we start counting. Okay, so we load it at 13. So the count up is clocked and the countdown is a logic 1. So that means that on every rising edge of the clock, the output count is incremented by 1. So what we're seeing here is it's going 13, 14, 15, 0, 1, 2. So make sure that you notice when the count is 15, the carry is a logic 0 for half of the clock cycle. So the carry is just giving a little blip for half of the clock cycle. And that's that cascading count. Now we're looking at it as if it's a countdown portion of the timing diagram. So the countdown is clocked and the count up is a logic 1. So that means that we're having the clock signal go into that down input and the count up, so the up logic is tied, or the up clock is tied to a digital constant. And on the rising edge of the clock, the output count is decremented by 1. So that means we're counting down. So here we see 2, 1, 0, 15, 14, 13. Now, make sure that you notice that when the count is 0, the borrow is a logic of 0 for half of the clock cycle. So again, we see that little blip on the borrow. All right, now this is very, very similar to what we're going to be looking at when we go to create the project for this, when we control our circuit with the 74LS193. So again, we have all of these set up. And we have the load and the clear loaded in here. If you look, up is connected to the clock, and so is clear. Down is connected to what would be a digital constant, as is the load. Now we don't have any inputs coming in here, all right, but we obviously would. And then we have our outputs of QA, QB, QC, and QD. Okay, and then we have the borrow and the carry. So what we're seeing here, okay, as we look at all of these inputs, is just the timing diagram. So this is just the sequence of what is happening as it goes through. So again, you can see as we hit various edges with the timing, we get different outputs.